Somewhere on Bainbridge Island, a stretch of ancient beach sits 23 feet above the water, stranded there in seconds by force powerful enough to lift solid rock straight out of Puget Sound. For decades, everyone assumed the real danger to Seattle sat offshore, locked beneath the ocean, waiting for one catastrophic subduction rupture. That assumption was wrong. New research says a hidden network of faults runs directly beneath the city itself, and one of them appears to have broken not centuries ago, but within the last 200 years, quietly, unnoticed underneath ground 4 million people now call home. Start with the beach. Geologists call it a marine terrace, a shoreline platform that used to sit at sea level. Today it sits high and dry above Restoration Point, a peninsula on the south end of Bainbridge Island. The rock did not erode into that position over thousands of years. It jumped there in one motion, sometime around the winter of 923 or early 924. Radiocarbon dating and tree ring analysis pin the timing almost exactly. The uplift was sudden, 6 to 7 meters, and it happened alongside a tsunami that swept through Puget Sound and landslides that tore into the slopes above Lake Washington. The quake responsible is estimated near magnitude 7 to 7.5. That number needs translation. A magnitude 7 earthquake releases roughly the energy of 32 magnitude 6 earthquakes combined, and this one broke close enough to the surface that the shaking above it would have been ferocious. Local oral tradition remembers it too, describing a shaking, water-dragging spirit tied to 5 sites along the fault's path, passed down long before geologists ever confirmed what had physically happened there. Scientists did not stumble onto this fault by accident. Gravity surveys in 1965 first hinted that something dense and structured lay hidden beneath the lowlands. It took until 1992 for a set of 5 separate research papers published together in the journal Science to finally connect the uplifted terrace, the tsunami deposits along the shoreline, the landslide scars above Lake Washington, and disturbed lake sediments into one unified event. A Pacific Northwest seismic network scientist later described the scene bluntly, joking that it would have been an interesting time to be alive only if you had a safe tent to sleep in. That is the kind of understatement seismologists use for an earthquake capable of throwing a shoreline out of the water. Here is the part that should unsettle you immediately. Most people who worry about a major earthquake hitting Seattle are picturing the wrong fault. The famous one, the Cascadia subduction zone, sits roughly 70 miles offshore, where one tectonic plate dives beneath North America. It last ruptured fully on January 26, 1700. A magnitude 9 event confirmed through both Japanese tsunami records and Pacific Northwest tree rings. Cascadia works through subduction, one plate grinding beneath another, friction locking the two together while stress silently builds for centuries until the rock finally gives way all at once. Cascadia is real and it is dangerous. But Cascadia cannot explain what happened at Restoration Point. That uplift happened directly beneath the city, not 70 miles out at sea. Something much closer to home did this, and that something is called the Seattle Fault Zone, a shallow crustal fault system that cuts straight through the Puget lowlands underneath Bainbridge Island, downtown Seattle, and the dense neighborhoods in between. That should have been the full explanation. A single known mapped fault caused a known historic earthquake. Case closed, except newer science has spent the last 2 years quietly dismantling that tidy version of events, and what is replacing it is far stranger than the original story. The first comforting number came from a University of Washington study published in the journal Geology. Researchers examined an 11,000-year-old shoreline near the fault and compared its deformation to the well-documented 923 event. Only that one earthquake across 11,000 years produced significant uplift. The implication sounded reassuring. If extra-large ruptures on the main fault are genuinely rare, then the recurrence interval might be longer than 5,000 years, not shorter, meaning more breathing room before the next one. One of the researchers even said the finding gave the region a buffer. But listen closely to what that study actually claimed, because it is narrower than it sounds. It says nothing about smaller earthquakes. It only rules out other extra-large shoreline lifting events. As the lead scientist put it, the study says nothing about large earthquakes, only about extra-large ones. A magnitude 6.5 quake, still devastating to a modern city, would not necessarily leave the kind of dramatic uplift these researchers were measuring. That gap between what the evidence rules out and what it actually proves is exactly where the next discovery landed. In January 2026, a separate study in the GSA Bulletin, led by USGS geologist Stephen Angster, revealed something the earlier picture had completely missed. Beneath Seattle's main fault sits a tangle of smaller secondary faults, blind faults that leave almost no visible surface trace on the ground above them. This was not the first time a hidden secondary fault had surfaced this way. Years earlier, a fault called Toe Jam Hill became one of the better documented examples in the zone only after airborne LiDAR sliced through dense evergreen forest and exposed a low scarp that foot surveys had walked past for decades. That earlier discovery taught researchers what to look for. Small, subtle steps in the landscape, easy to dismiss as erosion or old logging disturbance, could actually be the fingerprints of a fault that had never been cataloged. Armed with that lesson, Angster's team used the same laser mapping technique to strip away forest cover on Bainbridge Island and found something previously overlooked, a low, subtle raised terrace near a place called Lytle Beach, a stretch of shoreline lined today with quiet homes and a private golf course, the kind of ordinary suburban ground nobody would suspect of hiding an active fault. That terrace was the first clue. Chasing it led to ground-based magnetic surveys and eventually to a trench dug straight across the newly discovered scarp. Inside that trench, the team found glacial sediment roughly 15,000 years old, capped by lake deposits, capped by an old buried soil layer. The whole sequence was folded, bent out of its original flat shape. Angster was direct about what that means. The only way to fold layers like that is with a tectonic fault moving beneath them. He later admitted the discovery caught him off guard, calling it surprising precisely because the surface feature that led them there was so subtle, easy to have walked past, easy to have written off as nothing. The trench held two separate earthquakes, not one. The older event happened over 10,000 years ago. The younger one is the detail that should make you sit up. It occurred sometime after the year 1663, most likely in the early 1800s. That places a damaging rupture on a previously unknown fault less than 200 years before this video was made, on ground that now sits beneath one of the fastest growing metro areas in the country, and nobody recorded it because nobody was there yet to feel it. Nearby, at a second site called Vasa Park, the team found evidence of yet another earthquake on yet another secondary fault in a window that overlaps the older Lytle Beach event. Two separate blind faults, both capable of independently rupturing, both hiding beneath ordinary-looking hillsides and beachfront neighborhoods that residents drive past without a second thought. An earthquake scientist at the University of Washington who reviewed the work but was not involved in it called it exciting new research and made a point that reaches beyond this one island. He said the study shows there is room to accommodate smaller earthquakes, ones that will not dramatically lift a shoreline the way 923 did, but are still, in his words, big enough to be damaging earthquakes. He added that subtle features, small fault traces easy to have ignored, can end up being an essential part of the story, a lesson he said applies to other cities built on similarly complex ground, not just Seattle. Put those events together across the last 2,500 years, and a pattern starts to emerge that directly contradicts the reassuring 5,000-year buffer. These secondary faults appear to rupture roughly every 350 years. Angster was careful to caution that this is not clockwork. The estimate rests on a limited record, but the direction of the finding is unmistakable. The ground beneath Seattle is not quiet between major earthquakes. It is breaking repeatedly on structures scientists only recently learned existed. So which is it? Is the fault system dangerously overdue or comfortably rare? Here is where the apparent contradiction resolves, and it resolves in an uncomfortable way. Both studies are correct because they are measuring two different things. The University of Washington research concerns only the rare, extra-large shoreline lifting ruptures on the main fault, the kind that produced 923. The USGS research concerns smaller, more frequent ruptures on secondary blind faults that do not necessarily lift a shoreline but can absolutely produce a magnitude 6 or 7 earthquake directly under a city. One prior secondary fault rupture, documented separately from this new study, already registered close to magnitude 6.7. The reassuring number and the alarming number were never actually arguing with each other. They were describing separate hazards stacked on top of one another, one long interval and one short one, both active beneath the same streets. There is also a strange geometric detail that does not fit the tidy picture. The newly discovered Lytle Beach Fault dips south. Its better-known neighboring faults in the same zone dip north, tilted the opposite direction. That is not a trivial quirk. It suggests the underground architecture is more complicated, more fractured, and less uniform than the maps used for hazard planning have assumed. A city's earthquake risk model is only as good as its map of what is actually breaking underground, and that map has been incomplete, which raises an obvious question. Why is there a shallow, complicated, fractured fault system sitting directly beneath a major American city in the first place? The answer is older than almost anything else in this story, and it comes from a completely different kind of study, one that used gravity and magnetic field measurements instead of trenches and LIDAR. 55 million years ago, this stretch of coastline did not belong to the continent at all. It was a chain of volcanic islands, a piece of oceanic crust called Silesia, drifting toward North America and eventually slamming into it. When Silesia collided, it did not weld on as one clean, uniform block. Researchers publishing in the journal Tectonics found that the southern half of that accreted terrain appears to have torn away from its northern half, unzipping along a seam roughly where the modern Seattle Fault now sits. That ancient tear left a structural scar in the crust, a pre-existing weakness that younger faults could later reactivate. Let that sink in for a moment. The fault under Seattle is not simply a modern crack that appeared out of nowhere. It is a modern expression of a 55-million-year-old wound in the continent, reopening under contemporary tectonic stress from the Pacific Plate system pressing in from the west and south. The city was built, unknowingly, directly on top of a scar left behind when a piece of oceanic crust ripped itself apart. That comparison is genuinely unsettling, and it deserves to land before we soften it. But similarity across geologic time is not a forecast. An ancient rift zone does not carry a schedule. It explains why weakness exists here at all, why this particular stretch of the Puget Lowlands hosts a shallow, complex fault network instead of solid, uniform bedrock. It does not tell us when that inherited weakness will next release energy. The scar sets the stage. It does not set the date. There is a second reason the location matters beyond the fault's origin. The Seattle Basin, sitting directly above this ancient structure, is filled with kilometers of loose sedimentary rock rather than solid bedrock. Loose sediment behaves differently under seismic waves than hard rock does. It amplifies shaking, sometimes dramatically, the way a bowl of gelatin moves more violently than a block of stone when both are struck the same way. Seismic energy entering that soft basin can slow down, pile up, and resonate, rattling windows and shifting furniture across neighborhoods that sit well away from the actual rupture point. That means a moderate earthquake originating on one of these newly discovered secondary faults, shallow, close, and centered beneath a soft sedimentary basin, could produce shaking disproportionate to its raw magnitude number. Magnitude alone was never going to tell the whole story here. Depth, distance, and what the waves travel through on their way to the surface all matter just as much, and it is precisely those variables that current hazard maps are only now beginning to incorporate using the region's newly mapped fault geometry. It would be easy at this point to reach for a familiar and frightening comparison to call this region the next site of an inevitable catastrophic rupture. That is not what the evidence supports, and stretching it that far would betray the actual research. What the evidence supports is narrower and, honestly, stranger. A network of faults nobody fully mapped until recently. One of them ruptured within the last 2 centuries. The underlying weakness driving all of it traces back tens of millions of years, and the city sitting on top of it has grown into one of the most populous, fastest developing regions in the country, almost entirely within the modern seismic record's blind spot. Seattle has not experienced a significant, widely felt earthquake since 2001, when the Nisqually quake shook the region without producing anything close to the devastation of 9/23. That gap is not evidence of safety. Earthquake scientists who study this zone describe it plainly. The region can go decades without a notable event, and then, without warning, produce one. We do not know when they are going to come, one researcher put it, noting that the quiet stretch since 2001 is not unusual and offers no real guarantee about what comes next. The absence of recent shaking says nothing about what has been quietly accumulating on fault scientists only just found. None of this means an earthquake is imminent. It means the tools used to judge that question have changed. A hazard model built without knowledge of the Lytle Beach or Vasa Park faults was working from an incomplete map. A hazard model built without the ancient Silesia scar had no explanation for why this particular stretch of ground is so fractured in the first place. Both gaps are narrower now than they were 2 years ago, and both remain open enough that researchers describe this as unfinished work, not a solved case. So what actually happens next? Not in the sense of prediction, because nobody credible is predicting a date, but in the sense of what researchers are watching. Teams are continuing to run LIDAR surveys across forested areas of the Puget Lowlands, hunting for more of the subtle, low-relief scarps that revealed Lytle Beach in the first place. They are digging additional trenches, dating additional sediment layers, and checking whether other secondary faults in the network show the same, roughly 350-year rupture pattern or something different. Seismic networks continue recording every small tremor in the region, watching for clustering or migration that might indicate stress building along one of these blind structures. And basin modeling continues, refining exactly how strongly the soft sediment beneath downtown Seattle would amplify shaking from a rupture on any one of these now known, but still poorly constrained, faults. Each new trench, each new LIDAR pass, each newly dated layer of soil either strengthens the 350-year pattern or forces researchers to revise it. And that ongoing correction, not a fixed countdown, is what current science actually offers. The scientist who led the most recent secondary fault study was careful, almost deliberately undramatic, when summarizing his own findings. He said the study does not really change the hazard beneath Seattle. It only changes how well we understand it. That is a strange thing to hear after everything you have just learned, but it is also the most honest sentence in this entire story. The danger was always there. What changed is that scientists can finally see more of its shape. Go back to that stranded beach at Restoration Point one more time. For over a century, it has sat quietly above the waterline, a fixed physical record of one enormous, sudden event. For most of that time, researchers believed it was telling them almost the entire story of the fault beneath their feet. It was not. Buried nearby, hidden under forest canopy that LIDAR had to strip away just to reveal a foot-tall step in the ground, sat evidence of earthquakes the historical record never caught. Some of that evidence is barely 2 centuries old. Somewhere beneath the quiet streets and waterfront neighborhoods of a modern American city, instruments are still listening to a fault system that finished revealing its full shape only this year, and the ground has not stopped keeping its own record.